Hello, my name is Ryan Trask. I'm presenting pneumonia detection for my image pre-processing class, which is a part of the BCE program at the University of Maryland, a BioE program. Okay, let's get into it. Now, as the name implies, the objective of this project is to detect pneumonia in patients. How are we doing that? Well, we have single X-ray images of patients, and we're trying to train machine learning models to detect radionomic features in those images, use those features to predict whether the patient has pneumonia or not. Now I have two data sets to do this. I have a CXR data set, which is pneumonia negative images. So patients without pneumonia. And I have 800 of these images, and 704 of which have segmentations or masks of the patient's lungs. That means I have a binary mask, binary image of those patients telling me where their lungs are. And that's what a mask is. And I have another data set called the pneumonia data set. This is pneumonia positive patients. I have 501 of these patients and their images, but I have no segmentations for these. Now, for as you'll see later on in this slide deck, the segmentations are very important to the models I'm training. So I'll have to make my own segmentations for the pneumonia model, pneumonia data set. Let's get into it. Now, before we even think about doing our own segmentations, we need to pre-process our images. Now I select out the images that have masks, because that's the data we can train our model on to segment. So we have 704 of these images, pneumonia negative cases. Now I need to change up some things about these images. First, I changed the image range of pixel intensity values from 0 to 255 to 0 to 1. I did this because neural network training does a lot better on images that have values of 0 and 1. And that's also the same range as my binary mask, as you can see on the bottom right. So it's a lot easier to work with because I want the two images to agree with each other, basically. Also, I resize each of these images to from like 1000 by 1000 by 3 to 255 to 255 by 1. Basically, I changed it from RGB images to grayscale, and I reduced the X and Y dimensions, the number of pixels, down. Why did I reduce the number of pixels I have? That's less resolution. That is correct. I have less resolution in these 255 by 255 by 1 images, which means they're not as good as a representation of the patient's chest, but they're a whole lot less pixels to compute on my GPU, and I need to reduce the size of these images to actually do the training in my GPU. So that's a trade-off I had to make. Now, I took this data set and I split it into 3 separate sub-data sets. I have a training data set, which is 72% of the data. This is what the model will actually train on and learn from, adjusting itself and fitting to. Now, I have a validation data set, which is 18% of the data. This data set is what the model will check itself against while it's training to say, oh, did I mess up or not? If I did mess up, then it'll go back and try to fix itself. Now, I have a third data set, the testing data set, which is 10% of the data. This data set is for when the model thinks it's good and it stops training. I'll evaluate the model's performance with the testing data set after it's done training. Now, what model will I actually use to segment the pneumonia positive images? Now, I have, I'm going to be using a neural network, convolutional neural network model, which means it takes in an image. Now, specifically, I'm using a UNet model, which takes in an image and gives out another image. You see on the left that our input image is the actual chest image, while on the right is it's the mask or segmented image. So this model specifically for this sort of case. You see this UNet goes in, takes the input image, shrinks it down to a small representation at the bottom with a deep omics, and then it expands it back up with a skip connection reference and reconstructs image into a binary mask. And this is the model that I trained to segment the pneumonia positive images. Now, what sort of parameters did I use? I used the Atom optimizer with a learning rate of 0.0004, a mini batch size of 16, a loss function called focal binary cross entropy. Binary cross entropy because I only have segmentations of 0 or 1, lung or not lung. That's why it's binary cross entropy. What's the word focal mean? Focal means I had the model focus on hard to segment images while it was training. Now, as I was trained this model, you can see on the right, the loss, the validation loss is much higher than the training loss. This is because the model was overfitting. What was overfitting mean? It means that my model was looking at its training images and seeing things that weren't actually there, patterns that don't exist. So when I give you a series of numbers, 1, 2, 3, 4, you automatically know that the next number will be 5. But that's a useful feature. Or if I give you a random feature that doesn't make sense. If I give you like 5 t-shirts and we're looking at the colors. Well, what does the color have to do with the t-shirt? It doesn't mean anything. That's the sort of nonsense overfitting produces. So how did I mitigate this overfitting? I reduced the number of nodes per layer. So I shrinked the size of the model down. I augmented the training dataset images by images and masks by horizontally reflecting and rotating images semi-randomly. I batch normalized and batch normalized training images and masks in the encoder. And also in the encoder, I dropped out random neurons or nodes in said layers. And I also implemented early stopping criteria to stop the model early before it started jumping up and down meaninglessly without actually improving itself. As you can see on the right, which is my actual training and validation performance, I didn't completely eliminate overfitting, but it's much better than it was before. Now, I mentioned it before, a testing data set. Now my model is completely done training. I'm going to be testing this data set on images it's never saw before, and that's the testing data set. Now on this testing data set, the UNet model was 92% accurate with a 0.05 loss. It's about the same as the validation data set from before. And I had the UNet model segment all the X-ray images. You can see on the right here, examples of pneumonia positive and pneumonia negative segmentations by the UNet model. You can see it's a little rough around the edges. It's not perfectly accurate, like the mask I showed you before, but it gets the general shape, and that's good enough for what I'm going to be doing next. Now, I also decided to take these images and extract the features into quantified values through pyradianomics. You can see on the bottom there the actual features I decided to calculate manually These are like deterministic functions. I plug the image and the respective masks in to calculate the how, say, for example, mean, median, intensity, shape, features, all sorts of stuff. And these are all radionomics. And that's one model I'll be using to predict pneumonia. But another model I'll be using to predict pneumonia is a convolutional neural network model. Another convolutional neural network model. It'll be a smaller and simpler model, but it'll take the both the chest X-ray and its mask segmentations as its input, and it'll use whether the patient's pneumonia or not pneumonia as its output variable. Now let's talk about the simple CNN model I'm using. The first methodology, like you see in the middle there, the actual model itself, I have about 2 million parameters. It's a simple convolutions at the beginning, small parameters at the beginning, ramps up. I have some max pooling in between each convolution layers. Then I flatten them down into dense layers. I sprinkle in some dropout for overfitting prevention. Then I sigmoid to 1 or 0. So you can see on the left and right, I take the chest X-ray images, the mass as input, then I put it through the model, and I determine whether 1 or 0, whether pneumonia or not pneumonia. The simple convolutional neural network model. Now, like the other neural network, I have some basic parameters, an atom optimizer with a different learning rate, 0.0007, same mini batch size of 16, same loss function, but instead of the output variable being like a segmentation, its actual scalar value of 0 or 1. Now, like before, I also had some overfitting problems, but it's not as bad. You see it's trending very well on the right there. Accuracy is very high. It's almost at 1.0. That's 100%. As for mitigating the overfitting, I reduced the number of nodes per layer like last time. I add in a dropout function near the second to last dense layer. I also had early stopping criteria. But I didn't reduce the overfitting as much as the other model because I didn't have as much overfitting, and I didn't want to make my model underfit as a result, going in the other direction of it being incorrect. Now let's see how this simple CNN did on its testing set. It's at 97% accurate with 0.06 loss. It's a little worse on this testing set than on the validation data set, but I think 97% is very good. You see the visualization on the right. On the top, I have a classification report. F1 scores like how accurate it is. We have precision recall, support. We have accuracy. And on the bottom, you have the confusion matrix of which examples it got right or wrong. The diagonal matrix is true negative and true positive. True, when the model agrees with the actual true label. Now, the other diagonal, the two twos, is the false positives and false negatives when the model incorrectly predicted the labels. Now, that was one methodology. I'm using another methodology to predict pneumonia or not pneumonia. Specifically, if you remember before when I was doing the feature extraction with pyradionomics, this is what I was using it for. Instead of taking in input images, I'm going to be using, I'll be using actual numerical data. And instead of using a neural network model, I'll be using traditional machine learning models, such as support vector machine, k-nearest neighbor, random forest, logistic regression, naive Bayes, and XGBoost. Now, as for the data sets I'll be utilizing selected features as input/output independent variables. The output/dependent variable, what the model actually predicting will, as before, will be whether the patient has pneumonia or not. I split the data into two sub data sets: training and testing data sets, training for the model to actually learn from, testing data sets to evaluate the model's performance. And I split up, I remade each the sub data sets for each model as a form of cross validation. Now, before we do the feature selection, you can see on the top right there, that's the actual features that were collected. Now, for this sort of data, there could be a few problems with it. Two problems I checked for is missing values. That means values that simply don't exist. In this case, we use something called imputing. That means based off of the location of a NaN value relative to all other values, we'd be infer what that value should have been. And you can see on the left of the data set that is the actual patients, and on the top is the features. Another problem with this data set is when you look at the feature columns, they value widely in terms of their ranges. Like the first feature has like 120, 123, 49, 51. But the original first order energy has a big numbers. So if we just put these values into the rest of our model, it will over-select or over-represent those big numerical values, when in fact each feature should be equal in weight to each other. So what I did was I scaled the numerical range of all these features to have the same range. You can see that on the bottom, convert that, scale it. Now that my data is scaled and we've imputed any NaN values, we can now select for those features. Now, before I mentioned that we're selecting features to be our input variables. Which features are we selecting? Well, we're selecting the significant features. How are we going to do this? We're going to be doing it by reducing the dimensionality of the data through principal component analysis to measure the relative variability of the features. What does this mean? It means we take an individual data point and compare it to everything else, all the other data, and say, how different are you from the rest of the data? And if it's just average, you put 0. If it's very variable, we give it a big value. And once the PCA runs, we know how variable each data point is over several PCA vectors. Now that we have that data, we can then put these PCA vectors in accordance with each feature and compare it to the data before we actually reduce their dimensionality and measure for significance in various statistical tests such as Pearson correlation and Wilcox signed rank test. Why we put in statistical tests? Well, we want the p-values from those tests to determine how significant the features actually are. And of course, we want the features with very small p-values. Now, we aren't using 5% like usual because we're looping over so many PCA vectors and features. We have to divide that by 10 in accordance with the Bonferroni correction. And we select for features that are under 5% or under 5% divided by 10 over all PCA vectors. So you can see here that these 5 features have and they're 5 features at the bottom across all the PCA vectors have very small p-values. And that's what we selected for. And then we take this information, we go back to our original data, select those features. Now we know what's actually valuable and what's junk, and we throw away the junk. Now we take our data, our significant feature data, and we train our models, the models I mentioned before. And I looked over the testing data sets accuracy. And the best model was logistic regression with an accuracy of 88.6%. The worst model was naive Bayes with an accuracy of 80.2%. So there's not much variability, but even the best model, logistic regression, was not as good as the simple neural network model from before, but still pretty good. And as for visualization, if you look at my code, for each traditional model, I have a confusion matrix and a receiving operating characteristic curve. See on the right, those confusion matrix and ROC curve for the logistic regression. You can see it at 88.6%. And the confusion matrix, which I explained before. Now, as for the ROC curve, it's plotted as the true positive rate versus the false positive rate. Positive rate being pneumonia. Now that concludes our branching methodology for predicting pneumonia in patients with X-ray imaging. Thank you, and have a good day.